Hello everyone, my name is Hsieh-Yu. Today I would like to share with you our work, a control design for dynamic interactions between human, robot, and environment. So for this control scheme, we use variable admittance control with robust adaptive velocity control. So let's get started. Firstly is our background. Our background is here, physical human-robot interaction. So there are many types of collaborative robots depending on their task. So the cobot we use here is we mount a force sensor on the end-effector. And then we design a control scheme to transfer the human force into robot velocity. The feature of here is that the human can direct the motion of the robot, and normally the collaboration is compliant. In the literature, this is also often referred as collaborative robot in an augmentation mode. So here's one of the examples. The human can guide the direction of the robots based on their experience and judgment, and normally the cooperation is compliant. And then next is our research motivation and problem. Our research motivation here, if the human guides such a collaborative robot to contact an extra environment, we call this physical human-robot environment interaction. So right now, there will be an environmental force feedback on the force sensor. So all an environmental force feedback is defined as any external force on the robot minus the human force. This will cause unstable interaction. This is because right now the force sensor, including both human force and environment force, which is hard for a control design to regulate these two forces. So the interaction is even more unstable if the environment is a rich surface, and it moves in a multiple direction. And also, since the cooperation is compliant, it will become even more unstable. So here's one of the examples. We have a robot, we have a human, and we have an extra environment. So as you can see here, this is a rich surface for the extra environment, and the environment is moving in the in multiple direction. And as you can see here, since right now the contact point is dynamic, so it's challenging to reach a stable interaction. This is also because human arm is also a time variant impedance. So in this task, we will propose a control scheme to solve this unstable interaction problem. So next is our proposed control scheme. In our controller design, we have two loops. One is outer loop, where we use a variable admittance control for interaction control between three moving objects. That will be human, robot, and environment. And then in the inner loop, we have a robust adaptive velocity control. And the goal for this is quite traditional for better velocity checking performance in presence of the time variant signals. So this is the overall idea. And let's dive in for more formulation. Firstly is our outer loop. So here is our block diagram. So we have a human, we have a robot, and we have an environment. And in the outer loop, we have two parts. The first part is variable admittance control, where we have a variable mass and damping, which is quite standard. And our input here is two force. One is the human force, the other one is the environmental force. And for our update load, for the update load, we have two parts. The first one is the mass. We simply design the mass change in correspondence with the change variant of the damping. In other words, if the damping is larger, mass is larger, and vice versa. So the key things lies in the damping design. we have two factors. The first one is human factors. The second one is environment factors. And for the human factor, we use a very well-known design for physical human-robot interaction from this paper. The idea is we use the alpha, we use again times the human force times the direction of the robots. In this design, the collaboration can be adjusted based on human intended motion. So if you are more interested in more details about the physical human-robot collaboration, I will highly recommend you check this paper out. So in this paper, we have another feedback from environment. We just simply design as again times the absolute value from the environmental force. So in other words, when the environmental force is larger, damping is larger. When damping is larger, admittance is smaller. Then when admittance is smaller, the cooperation will be less sensitive in correspondence with the variance of the external force. So this one will help the robot to stabilize the interaction. So this is the key things from the outer loop. The rest of part is just force environmental force estimator. We use a very mature force estimator from this paper. I won't go through too much detail here, but the idea is that this force estimator, this momentum-based force estimator, we don't need any acceleration here, so the signal is cleaner. If you are more interested in more details, I will highly recommend you check this paper out. So this is the overall details in our outer loop. Next is our inner loop. Our inner loop is a robust adaptive controller. But before we dive in, I want to introduce you a sliding vector from this paper. This is for position control. And this is a very well-known sliding vector from this book. But as we can see here, we need a position arrows. But our control scheme for an outer loop, we don't have a position arrow because the output of the outer loop is a velocity command. So in this paper, we change this sliding vector into a sliding vector with an integral term. As you can see here, we don't need any position arrow, just simply velocity arrows. So the good thing about this sliding vector is that we can design the overall robust adaptive velocity control into a traditional form. So this traditional form, there are three parts. The first part is unknown dynamics. The second part is update for adaptive term. The last part is a sliding vector from our signal, so our from our new sliding vector. So since the robust adaptive velocity controller can design a traditional form, it's quite easy to prove the stability and passivity. And also, it's easy to prove the convergence of the checking arrow and force estimator. So if you are interested in more details, do check our paper out. Next is our experiments. So we choose pegging hole as our experiment. This is because when we insert the peg into the hole, if the tolerance is very small, it requires a very compliant interactions, a compliant cooperation, so that the human can accurately insert the peg into the hole. And then while at the same time, the interaction from the hole is quite strong, which cause more challenges on the task. So this is the pegging hole. And for our robot, we choose a 5 degree of freedom robot, where there are 3 degree of freedom Cartesian structure, and then 2 degree of freedom rotational joints and an end-effector. And this is our end-effector design. Look like this. We have a force torque sensor to measure the human force, and we have the operation holder for the human to grasp it. And we also have an instrument, which we call it environmental contact point. Like this is the peg inside the hole. And then in our environmental setup, we put the environment into a 2 degree of freedom moving platform, moving in this direction and this direction. So this is our first experimental setup. We have a hole here. The hole is just 0.4 millimeter larger than the peg. So as you can see, the tolerance is very small, which is more challenging because the environmental force will be very strong. And this is the piece of metal with the hole. And here's our result. As you can see, the moving platform, the platform is moving. Even the contact point is dynamic. The robot, also the human, can still confine and stably interact with the environment. This shows our result. And then in the second experiment, we choose two holes, two pieces of the metal. The goal is to check the continuous tracking and also contacting. So since the operator need to continuously contact two holes and also check the motion of the hole, this poses more challenges on task. And we also ask many people to try for our cooperation, such that we can see if our collaboration is general compliantly enough. So here's our results. As you can see, the operator will continuously contact and the two holes, and the whole platform is moving. And also everyone have a different habits using the robot, like the way they grasp the holder. But as you can see, everyone can complete the task. This one shows our collaboration is compliant and our interaction is stable. So this is our second experiment. And we also compare our proposed method with a traditional method where a constant admittance is used. As you can see from this chart, the time is much lesser, and energy, human force, and velocity tracking area. Our proposed controller is all outperform the traditional one. And then this is the second one. Then lastly is our third experiment. We have the wall with a rich surface with a sand metal, but this time the human have to complete a task with an eye mask on the surface. We call it blind insertion. And then he has to contact the environment with a very fast approaching speed. So here's what I mean. As you can see, the human have a eye mask on the surface, so he cannot see. When he contact the environment, he use a very fast speed. Even under such a large force and speed, the interaction is stable. And also, since he cannot see at all, the only sense he has is the sense of touch. As you can see here, the cooperation is compliant, so that he can slowly search in the hole. And because the interaction is stable, he can insert the hole stably. So this concludes the performance of our controller. So lastly is our conclusion. In this paper, we try to solve the issue where the dynamic interaction will happen between the human, robot, and moving environment. And this dynamic interaction may cause unstable interaction. So we propose a control scheme to address this issue. The goal of this control scheme is to allow the human operator to be able to stably contact the moving environment. And also at the same time, the cooperation is compliant so that he can follow the motion of the hole. Yeah, this is all of our presentation, and thank you.